want to start with a demo, which will also serve as example for, if you switch to the screen please, which will also serve as example for an algorithm that is non-hierarchical but fuzzy, namely the Gaussian mixture model. So I have some data set here. I randomly throw some Gaussians in there. They all have the same covariance matrix to start with. And we will now look at an algorithm that is similar in spirit to the k-means clustering. So we first estimate to what extent each observation belongs to or can be explained by one of the Gaussians, and I'm going to show this by a color coding. So you now see that where the Gaussian has the greatest posterior probability, these are fully green. Where the red has by far the greatest probability, greatest posterior probability, these are fully red. And then we have these intermediate colors. And now given these assignments, we can now update the clusters of the Gaussians, just as we did in the k-means algorithm. In the k-means algorithm, the memberships were crisp, so they were 0 or 1. Here they will be weighted. So you know, here I have 50% of this point belonging to the red, 50% of it belonging to the blue, and it doesn't belong to the green one at all. But then we will have other points that actually, or if I had a point very far down here, it would be equally explained by all three. So we will have a weighted update. And so what we have observed are just the points. What we have put in is this model, 3 Gaussians, and which point was generated by which Gaussian, because that's part of the modeling assumption, that is the hidden variable. That is something we will try and infer using the EM, the expectation maximization algorithm. So now I'm going to update the Gaussian centers and the covariance matrices. Now I can re-estimate the memberships, so the color changes, and then I can update the Gaussians, and I can keep iterating this. And so on. So this is an example of an algorithm that involves hidden variables, and expectation maximization is one way of dealing with those. So expectation maximization, or EM, is a strategy to find the optimal parameters theta in a model comprising both observed or visible variables and latent or hidden variables H. And in this part of the lecture, I'm going to follow closely a new fine textbook. This has come out a few weeks ago, written by David Barber, called Bayesian Reasoning and Machine Learning, and there's also a PDF version available online. And the development that I'm giving here, except for some details later in the Gaussian mixture model, follow exactly this Barber Bayesian reasoning textbook. I like it. I like this book because it really goes through the proof step by step and makes very explicit how things work. So what do I mean by optimal? Optimal, I mean as the ones that maximize the marginal likelihood. However, we have a model that involves both the visible and hidden variables. So I can obtain the marginal likelihood by integrating out. I'm here assuming that the hidden variables are continuous, so I'm putting an integral and not a summation sign. So this would be the joint likelihood of a single observation where the visible variable takes this value and the hidden variable takes that value given the parameters theta. And now by integrating out my hidden variable, I end up with the marginal likelihood. And the best parameters, since only the variables v are observable and the hidden ones are not, the optimal parameter is then going to be the one that maximizes this marginal likelihood. Now, this maximization, in particular, thanks to this integration here, can typically not be done in closed form. And, well, to solve this problem, we could use, or we can use, any black box nonlinear optimizer. And in fact, this is the method of choice. When the M step, which I will define below, cannot be expressed in closed form. Now the strategy of EM, or variational EM to be more precise, is to avoid this integration, this integrating out, which may be difficult, of the hidden variables. So it avoids marginalizing over the hidden variables. Instead, we will try and estimate the hidden variables given some starting value for the parameters, and then given this new estimate of the hidden variables, we will re-estimate the parameters, and so on. So we iteratively optimize over the hidden variables, or the probabilities of these hidden variables, and the parameters instead. And we will do two things. We will first look at a lower bound on this marginal likelihood and show that the lower bound can be increased. And then secondly, we will show that not only the lower bound increases, but actually the likelihood of our current parametrization does too. Now, I need two intermediate results. So to obtain this lower bound, we will need the Kullback-Leibler divergence and the Gibbs inequality. And I want to use 2 or 3 sheets to go over these. So first, the Kullback-Leibler divergence. Is a popular measure for the distance between two distributions Q and P. And it's been found a couple of times. It's also known as relative entropy or as the information gain. It has a couple of other names too, and it is, for example, related to the mutual information as follows. The mutual information between two variables, between two random variables x and y, is given by the Kullback-Leibler divergence between the joint distribution and the product of their marginals. And something like this we had, by the way, seen in the very beginning of the semester when we were talking about distance covariance. Now, so the Kullback-Leibler divergence measures a dissimilarity between distributions Q and P. It's not a metric, however. For example, it is not symmetric. So this is why I cautiously call it dissimilarity. And so what is it? Kullback-Leibler divergence between Q and P. If I want to be agnostic about whether I am dealing with discrete or continuous variables, I can formulate it as follows. It's the expected value of log Q of x minus log P of x, where the expectation is taken with respect to this distribution Q. And the Gibbs inequality will tell us that this is either 0 or more. And it can only be evaluated for Q of x and P of x that are larger than 0 for any x and which are normalized. So I can write it for the discrete or the continuous case. Yeah, when you get a 0 log 0, you interpret this as being 0. So it is also used for distributions that become exactly 0. So I was saying that this part is interpreted as 0 when we have 0 log 0, but if this is non-zero and this goes to 0, yes, we have a problem. Yeah. So they should have the same support. You're right. Okay, and so you see here we had an expectation, and this is the definition of the expectation operator. So I take the function here, log q of x minus log p of x, and then I sum over all the possible values and I weight with this probability mass function. Or in the continuous case, I have an integral. Okay. Yes. You can, in information theory, people typically take the binary logarithm, and then you talk about bits, and outside communication, it's the natural logarithm, and then the unit is in nats. So one interpretation of this is when you do optimal coding, how many extra bits you need by using the one distribution to code when you want to transmit samples from another distribution. Okay. Then for the Gibbs inequality, this lower bound that we use can be derived using either the Kullback-Leibler divergence and the Gibbs inequality, or it can be used using Jensen's inequality. Here we're using Gibbs. So we are lower bounding the logarithm. Sorry, upper bounding the logarithm by saying the log of x is less than or equal the tangential function here, x minus 1. And now I can replace x by the ratio of my distributions. So I can write log p of x by q of x. And I can multiply by the non-negative q of x, which will give me q of x log p of x minus q of x log q of x. And now, depending on whether it's a continuous or discrete variable, I can integrate over or sum over both sides. And on the right-hand side, you see if I sum or integrate over p of x, this will give me just 1. And if I sum or integrate over q of x, this will also give me just 1. So this vanishes. And here again, using this notation, which comprises both integration and summation, I can write it as log p of x minus log q of x. And the expectation is taken with respect to this distribution here. And if I now multiply by minus 1, I get a minus here, a plus here, a greater than or equal 0, and that amounts to the Gibbs inequality. So multiplying with minus 1 on both sides then gives this thing here, the fact that the Kullback-Leibler distance or divergence is always non-negative. Okay, and this we can now use to derive a lower bound on the marginal likelihood. We find a lower bound on the marginal likelihood, again starting with a single training example. For a single training example, we get that KL of, I'm using a helper distribution Q of H given V. So I'm using the fact that this will be non-negative, and I'm inserting the definition here. This is all with the aim of getting an expression that involves the marginal likelihood, which we will have 2 or 3 lines further down. So this is, P is the true distribution, which is unknown, and Q is a variational distribution, variational means that this is a parameter of an optimization problem that we're going to solve. Okay, and I'm now rewriting this thing here. So we know that in general the conditional is given by the joint divided by the marginal. You know, if you multiply with the denominator here, you obtain the form that you're perhaps more used to seeing. And I'm just inserting this way of writing it, and my Kullback-Leibler distance, the same arguments as above, now becomes, the first term stays the same, and now I have the numerator here. But this expectation is with respect to the hidden variable h, and this last term here is independent of h. So I can pull it out of this expectation. And if I do pull it out, and if I bring the remaining terms on the other side, I find that log P of V given theta, which is the quantity of interest. This is my marginal likelihood. Is bounded from below as follows. Full stop. here's our lower bound on the marginal likelihood. And well, this last term is important, so it has a name of its own. This is the expected complete data log likelihood. So it's a log of likelihood. It's complete because it involves both the hidden and the visible variables. And it's expected because we take the expectation with respect to this variational distribution over my hidden variables. Or in physical terms, the first term here looks like an entropy, and the second looks like an energy. So this was for a single training example, and if we now use instead n training points, and assuming they are independently distributed according to the same distribution, then I find that the log here of the joint probability of all these observations, I have n of them, so I multiply all of these probabilities and taking the log then gives me a sum. And now on the right hand side I'm using the same but for as above, but for each observation. So I have for a total of n observations minus this entropy term. Plus that energy term. Sorry, running out of space here. Good. And now if you look at the derivation again, you see that so we started up here on this page. You see that the bound becomes tight, or it becomes an equality when here the first term in the Kullback-Leibler divergence is the same as the second term. To make this lower bound tight, we need to set this variational distribution Q of Hi given Vi to be the same as this true distribution P of Hi given Vi and theta. So now we want to make this lower bound as large as possible, and we have a positive sign here, so we want to make this term here as large as possible. So to push up this lower bound, we need to iterate the E step or expectation step where we fix the parameters, we fix theta, and find the variational distribution that maximizes equation from above, and we alternate this with an M step or maximization step. Where we this time fix the distribution over the latent variables, or fix the variational distributions, and then find a new parameter estimate that maximizes this equation 1. The big one just up here. So altogether in EM, rather than integrating out the hidden variables, we try and estimate them given the parameters, and then given these estimates we optimize for the most probable values of the hidden variables, and so on. So far we've shown that we push up the lower bound, but we have not proven that this really increases the marginal likelihood also. And that is a second important property that we need. So I'm using now the values that made the bound tight, but you see that we now iterate this, so I'm going to give an index old to the old parameter set. So for the lower bound we get the following. The probability of the visible variables given the new parameter estimate should be, so I'm copying the old expression for the lower bound, but introducing now the distinction between old and new parameter estimates. So what I've done here is I've used the previous estimate for my hidden variables as my variational distribution. So this is where I previously had this distribution Q, and I've replaced Q by this best estimate, the one that made the bound tight, using the old values of my parameter estimate. Old, old, new, and old. And well, we can similarly write a bound for the old parameters, or for the old marginal likelihood. And that is now not an inequality, but a strict equality. And the first term is the same. And the second term is almost the same, except I have an old there. So spot the difference, huh? And I can now subtract the two equations from each other. So the first one minus the second one. This is the new and the old marginal likelihood. The first term was the same, so it cancels to 0. And the second term has the form of a Kullback-Leibler divergence, namely the divergence here between the old and the new complete likelihood. Okay, and being a Kullback-Leibler divergence, this must be non-negative, and hence we so because this is either 0 or larger than 0, we see that here the new marginal likelihood minus the old marginal likelihood it at least cannot decrease. And in most instances it will increase. So EM at least cannot decrease the marginal likelihood. So that was the second part of the argument that we needed to see why EM is useful. So we have a lower bound that we push up, and we show that the marginal likelihood becomes at least no worse, and in practice it becomes quite a bit better, especially in the first steps of EM. So convergence is often quite fast for the first steps. To fully converge it can take a long time. Good. A few comments. Okay. Importantly, we did not prove anything about coming to a global optimum or convexity or something like that. So EM finds only local minima. And, well, depending on the model, you can really end up in very bad local minima if you initialize poorly. Then we had the two steps, the E step and the M step. The M step is more forgiving, so using just an approximate or a partial M step is possible. Meaning that any operation that increases, let me write the energy for short. You remember I said one can be interpreted as entropy, the other one can be interpreted as energy. So any operation that increases the energy, or if you don't want to look back, I write it down again, which term that was. So any operation that increases the energy works all right. Of course, if you can find those parameters that actually maximize it for your current estimate of hidden and visible variables, this will be better. But really, any improvement here is just fine. In contrast, the E step is more subtle. So if you look back at the proof, our proof worked, or it hinged on really making the bound tight. And if we don't do that, so if we use a partial E step, that still does guarantee an increase of the lower bound, but it does not guarantee or does not guarantee this monotonicity property of the marginal likelihood. So if we use the partial E step, this would no longer make sure that our marginal likelihood cannot decrease. Okay, as a final comment, there is a further extension to this variational EM, namely variational Bayes. And with the EM algorithm, we are in the 1960s or so. With the variational Bayes, you are smack in today's research. So people have started coming up with procedures a few years ago, but this is still a hot topic of current research, how to find better inference schemes here. So in the variational Bayes, you use a prior and posterior distribution over parameters rather than a single value. And you then also need a distribution over your hidden variables. And the following independence or factorization assumption is then usually made, namely that your distribution over hidden and visible variables given your parameters can approximately be factorized as follows. So as a product of an independent distribution over H and an independent distribution over your visible variables. And you then iterate the following, an E step, where you find a new distribution of your hidden variables, and an M step where you find a new distribution over your visible variables. So this assumption here in a graphical model, this would amount to eliminating all the edges that somehow connect your hidden and your visible variables. And I call it an extension. I could also have said it's a generalization because it specializes to the variational EM. When the prior over your parameters is uninformative, and when the posterior is approximated by a single point rather than a full distribution. Good. Now, this was very abstract, I know. After the break, we will apply this to the Gaussian mixture model, and I hope that this will give some more intuition for these two steps. In the break, there was a question regarding the nature of this term. So, in general, a model will simply be a function involving the variables v, the visible variables, also involving the variables h, the latent or unobservable ones in case there are any, and of course the parameters. And if I now fix the parameters and compute the value of my function for a given possible realization of v, then one would call this the probability. So the probability of v given theta, and vice versa. If I fix v by, for example, taking the number that I got from some measurement, and I'm now looking for the parameter theta that best fits my model to the data or that best explains this observation, then I keep v fixed, and now theta is the function, and then this entire term becomes a function of theta, and in that case I call it a likelihood. Okay, so it's just it's the same equation fundamentally, but you call it probability or likelihood depending on which term in the equation you fix.